Our focus for this class is on the equations of uniformly accelerated motion, just like you can see on the screen. Okay, equations of uniformly accelerated motion. Let us take, for instance, suppose an object is accelerating uniformly with a velocity of u, and this velocity is called the initial velocity. Okay, initial velocity of u, and then to a final velocity of v. Final velocity is equal to v at the end of the motion, and this motion took a particular time t. So suppose this is what we have. Okay, we can therefore describe acceleration by saying that acceleration, remember from our previous lecture, we said that acceleration is equal to the change in velocity. All right, so we can say velocity change all over the time taken, and velocity change is actually the difference between the final velocity of the object and the initial velocity of the object. So we know that the final velocity of the object is v and the initial velocity is u, then all over the time taken t. Okay, we can represent acceleration, or we can denote acceleration using a small letter a or any other symbol you feel like. All right, but in most cases we use small letter a. So we can say that a is equal to v minus u all over t. If we decide to cross multiply so as to have a linear equation, we can say that acceleration at is equal to v minus u. And if we make final velocity the subject of the formula, we have v to be equal to u plus at. And this is the first equation of motion. We can call this equation 1. All right, this is our first equation of uniformly accelerated motion. Now let us consider another scenario. Okay, now considering a distance traveled, let's say the object traveled a particular distance with a uniform acceleration. Okay, now let us call the distance. The distance is denoted by, let's say, s. Okay, now if the acceleration is constant, and by now I'm sure you know what constant acceleration is. If the acceleration is constant, then the velocity increases uniformly. So therefore we can say that average velocity is equal to the half of the initial plus the final velocity. Okay, where initial velocity is u and v is the final velocity. So average velocity, let's call it VAVE, is equal to u plus v all over 2. Okay, u plus v all over 2. Remember we had equation 1 before. Let us call this equation 2. Okay, let us call this equation 2. And from equation 1 gave us v equals u plus at. All right, and our average velocity, if we decide to put equation 1 inside equation 2, okay, so if you put equation 1 inside equation 2, we have our average velocity will be equal to 1 over 2 into u plus at, where this is the first equation of motion, which stands for v. It's over here. Okay, now if we continue, we have that the average velocity is equal to 1 over 2 into 2u plus at, because u plus u gives us 2u then plus at. All right, but let us take note that the distance traveled s is equal to the average velocity times time. Recall that we said that velocity is equal to distance s all over time. I'm sure you know that velocity is the rate of change of distance, or displacement rather, with time. Okay, and in most cases we use displacement and distance interchangeably, though they are not the same thing. Okay, they are not the same thing at all, so don't make that mistake. All right, so but analytically, the average velocity is equal to the distance traveled or distance covered over time. Okay, so if we cross multiply, we have that the distance is equal to average velocity times time. All right, so if we have that, we can substitute for distance in acceleration, in average velocity rather. Okay, now this invariably, okay, since we have that s equals v average times time, and we know that average velocity equal to 1 over 2u plus at. So we can say that s is equal to 1 over 2u plus at times time. Okay, so if we open the bracket, we have s to be equal to 1 over 2ut plus at squared. Okay, because 1 over 2 is multiplying everything in the bracket. Okay, so we can decide to split them into two by saying s is equal to 1 over 2 times 2ut plus 1 over 2 times at squared. So if we do that, 2 can cancel out, this cancels this, and we are left with the equation s equal to, from the previous one, ut plus half at squared. Okay, s equals ut plus half at squared, and we can call this equation, okay, we have equation 2 already, so let us call this equation 3. Equation 3. All right, now from the first equation, which is equation 1, and the average velocity from equation 1, which is v equals u plus at, rather u plus at, and we also have that average velocity is equal to 1 over 2u plus v, 1 over 2u plus v, and we said that acceleration a is equal to v minus u all over t. Therefore, if we make t the subject of the formula in this particular equation, that's in the acceleration equation, we have that t is equal to v minus u all over a. T is equal to v minus u all over a. So if we can decide to call this equation 4. All right, now if we then decide to substitute the value of t, okay, the value of t into the distance equation, which is this, into this equation, then we have that distance s, remember distance s is average velocity times time, and we say that average velocity is equal to 1 over 2 this is equal to 1 over 2u plus v. So we have that s is equal to 1 over 2u plus v, and then times time is no longer t but v minus u over a. So if you do that, we have v minus u all over a. All right, if we take the LCM, we have, or if you just multiply through, there's no point taking the LCM. If you just multiply through, we have s is equal to u plus v multiplied by v minus u all over 2a. Okay, then opening the bracket gives us, if we open the bracket and let us infuse two steps in one. If you open the bracket and cross multiply, we'll have that 2as is equal to uv, u times v, uv minus u times u, that's u squared, okay, plus v times v, that's v squared, then minus, because plus times minus gives minus, then minus uv. Okay, then this is what we have. And if we decide to cancel out, you agree with me that this will cancel this out. uv will cancel minus uv out. It's just like saying minus 1 plus 1. It will give us 0. Okay, and we will be left with 2as equals minus u squared plus v squared. Minus u squared plus v squared. And if we make the final velocity the subject of the formula, we'll be left with this equation, which is v squared equals u squared plus 2as. And which equation? What equation? Yeah, this, let us call it equation 5. Equation 5. Now, we can decide to bring out the most important equations that we have, which are from equation 1, okay, equation 1, equation 3, and equation 5. Equations 1, equations 3, and equations 5. So we have from equations 1, 3, and 5. We have the equations for the uniformly accelerated motion, which is v equals u plus at. We have s equals ut plus half at squared, and we have v squared equals u squared plus 2as. So we can finally call this the first equation of motion, the second equation of motion, and the third equation of motions. Okay, now these are the basic equations of motion. Now, other equations can be derived from this, as we saw while we were deriving the equations here. And the other equations are, so let us say others are a equals v minus u over t. Okay, we also have s equals u plus v over 2 times t. We also have s equals vt minus half a t squared. So these equations are also very important depending on the parameters given. All right, so both the three basic equations of a uniformly accelerated motion is v equals u plus at, or r, v equals u plus at, s equals ut plus half at squared, and then v squared equals u squared plus 2as. In conclusion, I would like to make few notes so that whenever you're solving or whenever you come across a problem, you know how to tackle it. The first note here. 1. When an object is said to move or accelerate from rest, okay? When an object moves from rest, then initial velocity is equal to 0. That's the first thing you have to take note of. Okay, when an object starts from rest, initial velocity is equal to 0. The second note is that when an object comes to rest, the first one was it started from rest. But the second condition, or the second case we can find, is that when an object comes to rest or stops, then as it comes to rest. So we have the final velocity to be equal to 0, right? And the third case is when a body's velocity is constant, that is, when the velocity is not changing at all, then we have our acceleration A to be equal to 0. And this is when the body's velocity is constant. And with this, we have come to the end of this class on the equations of uniformly accelerated motion. I'm sure you have a lot of questions for me. Keep them coming, as you can drop them on the platform for me to attend to them. We'll see you in our next class, where we'll talk about some other interesting concepts in physics. Till we meet again, bye.